initial value problems and boundary value problem. So consider an nth-order linear differential equation, and we call it initial value problem or IVP if it satisfies the following. So first of all, you have the nth-order linear differential equation, an of x times the n derivative of y with respect to x plus another expression in x times the nth minus 1 derivative of y with respect to x plus the rest of the terms times a sub 1 of x y prime plus a sub 0 of x, y, and on the right hand side you have a function like g. It must satisfy the following condition. When you plug in x sub 0 in y, you get y sub 0 back. When you plug in x sub 0 in y prime, you get y back. And you continue this process, and eventually you plug in x sub 0 into nth minus 1 derivative of y, and you get y n minus 1 back. For a problem like this, we're looking for a solution on some interval like I, which contains x sub 0. And at the same time, it satisfies the differential equation and an initial condition as well. So this is the definition of initial value problem. We already seen examples for second order linear differential equation with initial value. Please note that the curve must pass through the point x sub 0 and y sub 0 and has slope y1 at that point. Let's take a look at the theorem. Existence of a unique solution. So what do we have here? Suppose a sub n minus 1, a sub 1, a sub 0, and g of x are all continuous functions on interval I, and suppose the leading coefficient is non-zero. If x equal to x sub 0 is any point in the interval, then a solution like y of x of the initial value problem exists on the interval, and it is indeed unique. So make sure to check the continuity, and the leading coefficient is non-zero. And if you have x sub 0 is any point on the interval, then a solution y of x of the initial value problem exists, and it must be unique. For example, take a look at the following differential equation. 3 times the third derivative of y plus 5 times the second derivative of y minus y prime plus 7y is equal to 0. First of all, this is a third order differential equation with constant coefficients. You have 3, you have 5, -1, 7. The right hand side, it is just 0. It says, hey, if I plug in 1 in my y, I get 0 back. If I plug in 1 in the first derivative, I get 0 back. And if I plug in 1 into the second derivative, I get 0 back. This is just a coincidence that all of these are zeros. It indeed has the trivial solution y equal to 0. If I take the first derivative of 0, it is 0. The second derivative of 0 is 0. The third derivative of 0 is 0. So if I plug in 0 plus 0 minus 0 plus 0, it indeed equal to 0. So y equal to 0 satisfies this differential equation. And because the third order equation is linear with constant coefficient, it follows that all conditions of the theorem are met. All of these are constant values. Constant functions are all continuous. So we have continuity. And at the same time, this solution satisfies this differential equation, and y at 1 is equal to 0. Y prime at 1 is equal to 0. Y prime at any point is equal to 0. So if you take the second derivative, it's also 0. So y equal to 0 is the only solution or the unique solution on any interval containing 1. Okay, we just learned about this theorem. Let's take a look at another example. You can easily verify that y equals to 3 e to power 2x plus e to power negative 2x minus 3x is a solution of the initial value problem. Here you have on the left-hand side the second derivative of y minus 4y equals to 12x. It says, hey, y at 0 is equal to 4 and y prime at 0 is equal to 1. You can take the first derivative, second derivative of this function, plug it into the left-hand side, and after simplifying, it becomes 12x. Since all of these are continuous, especially 12x, it's just a linear function. It is continuous everywhere. And the leading coefficient, which is just located here, is non-zero. On any interval containing x sub 0, we are good with the condition of this theorem. So we conclude that the theorem gives us a function that is a unique solution on the interval I. So as long as these conditions are met, we are guaranteed a unique solution for the initial value problem. So please note that you can observe that an ordinary differential equation might not have a solution or unique solution. That is absolutely fine. But when we impose initial and boundary conditions, uniqueness can be guaranteed. If the condition for a given differential equation relates to a single x value, the conditions are called initial conditions. And the differential equation is called the initial value problem. For a boundary value problem, if the conditions for a given differential equation relates to two or more x values, the conditions are called boundary conditions or boundary values. The problem of finding solution of a differential equation with its boundary conditions is called boundary value problem. So another type of problem consists of solving a linear differential equation of order 2 or more, in which the dependent variable y or its derivatives are specified at different points. A problem like this, a sub 2 of x times the second derivative of y plus a sub 1 of x times y prime plus a sub 0 of x y equals to g of x, and y at a is equal to y sub 0 and y at b is equal to y1. So now please note that we are using a and b. It's not the same value. It's called a boundary value problem or BVP. The prescribed values of ya to be y sub 0 and yb to be y1 are called boundary conditions. A solution of the following problem is basically a function satisfying the differential equation on some interval I containing two values a and b. So please take a look at this visualization. These are the solution curves of the boundary value problem that passes through 2 points A and B. Okay, let's take a look at one example for you here. A boundary value problem can have many, one, or no solution. We saw that two-parameter family of solutions of a differential equation, the second derivative of x plus 16 times x equal to 0, is of the form x equals to c1 cosine 40 plus c2 sine 40. You can again take the derivative, the first derivative, take the second derivative of this function, plug that in here, plus 16x. After simplification, it is equal to 0. Suppose we want to check the solution of the differential equation that further satisfies the boundary conditions x at 0 is 0, x at pi over 2 is equal to 0. First of all, please observe that c1 times cosine of 0 plus c2 times sine of 0 is equal to 0. So what's the meaning of that? It means that C1 must be equal to 0. So x equal to C2 sine 4t. So when you plug in t equals to pi over 2 and you solve this equation, C2 times sine of 2 pi becomes 0. It satisfies for any choice of C2 since sine of 2 pi is always 0. So the boundary value problem, the second derivative of x plus 16x equal to 0, x at 0 is 0, and x at pi over 2 equal to 0 has infinitely many solutions, right? Because of the choice for C1 and C2. You can visualize some of these values using different values for your C2. If C2 is equal to 1/4, this is the pink graph. When C2 is equal to a half, you have a yellow graph. When C2 is equal to 1, you get the green graph. So as you can see, the amplitude of our solution curve is changing. All depend on the value of C2. That's how you end up with infinitely many solutions.